Okay, thank you, and thanks to the organizers for giving me the possibility to present this work. So I will talk about orbital degeneracy loci, which is a joint work with Sara Angela Filippini, Laurent Manivel, and Fabio Tanturri. So orbital degeneracy loci are certain possibly singular subvarieties of a given variety, which are constructed starting from a model, and the model will be usually an orbit closure inside a representation of an algebraic group. So to each such model, we can associate an orbital degeneracy locus. And I will try to explain that using orbital degeneracy loci, and maybe I will say sometimes ODL, we can translate the problem of constructing some interesting varieties into the problem of finding some varieties with a vector bundle on it with some fixed invariance. And also another motivation for this work is that we want to construct varieties which are not zero loci in general. So I will present some motivation for this work, and then I will give the definition of orbital degeneracy loci, and I will give some examples. And in the second part of the talk, I will try to explain that we have some tools to study them, and I will, if I have time, I will give some applications. So, okay, I will put the motivation here. So the motivation for us was to construct new interesting varieties. So let's say D. So we concentrated on Fano varieties, so minus KD ample, and varieties with trivial canonical bundle, so special varieties. So for Fano varieties, we have a classification of families in dimension 3, but there is an effort to extend this classification to higher dimension, so dimension 4, or to singular Fano varieties. And on the other hand, for what concerns varieties with trivial canonical bundle, we already saw some of them in the morning courses, in Alessandra Sarti's courses. So there are K3 surfaces, and more generally, IHS manifold, of which not many explicit examples are known. Like, and then also there is an interest in constructing Calabi-Yau varieties. So maybe Calabi-Yau varieties, especially in dimension 3 for their importance in mirror symmetry. So let's say classically, you can do many things, but one way to construct subvarieties is to consider zero loci. So zero loci. So you have a vector bundle on your variety X. Vector bundle. You take a section of this vector bundle, and then you consider the set of points where the section is 0. Okay, this is classical. And you have some nice properties. So if E is globally generated, with GG, and S general, then you get that the zero locus is smooth. You have the adjunction formula to compute the canonical bundle of the zero locus. So, which is the restriction of a line bundle on all of X. This is important. And then, for example, you have the Kosul complex. complex, resolving the structure sheaf of your zero locus. So, for example, if you want to construct varieties with trivial canonical bundle, you just need to find a variety X and a vector bundle E, and you can ask the condition that this bundle on all of X is trivial, and then you get a variety with trivial canonical bundle. So just to say that Mukai used zero loci to interpret the known families of Fano threefolds, and so with orbital degeneracy loci would be a generalization of also of zero loci, and we will try to understand when we have this property so that we can control in a certain way the canonical bundle. Okay? So now we'll explain the definition of orbital degeneracy loci. So I said we need to start from a model. So the model, we take a G, an algebraic group, maybe let's stop here. V, a G representation. And then we need to fix a closed G invariant subvariety of V. Okay, so we call them orbital because usually one can take the orbit closure, one orbit closure, the closure of an orbit. Then what you want to do is to relativize this model. So you pick variety X, which will be the ambient space for the degeneracy locus. So in the results later, it will be smooth and projective. And you try to relativize this model. So what you can do, the good notion is to relativize the algebraic group is to take a G principal bundle F. So it is a locally trivial fibration over X. So we have trivialization open subsets on which F is trivial, G times U, and the map is just the projection. And then we have an action of G over F, which preserves the fibers and is just multiplication on the fibers. Okay, this is classical. And this principal bundle actually allows to relativize this model over X. So it defines a functor. So F underscore, which takes any G variety Z and associates to it a locally trivial fibration over X with fiber Z. Okay, and actually the construction is explicit. So F of Z is the quotient of F times Z, quotient by the relation given by the diagonal action of G on this space. So for any F in F and Z in Z and G in G, we have this point. So we act with G on Z is equivalent to F G Z. Okay, and so one can can see that, okay, we've got from this product, we've got the projection toward F, and then towards X, and actually, when we take the quotient, this map is still well defined, and so it's a locally trivial fibration with fiber Z. So this can be seen explicitly because over a point X, so the fiber is just set of points. So in the fiber of X, so let's say X G prime Z, and then you act with the group to get the identity here, and so you move inside Z. Okay, so now we had the inclusion Y inside V. This becomes Fy inside Fv. And so this is a vector space, this is a vector bundle. Okay, so I'll just make a picture. So this is X, this is Fv. This little X, a point. So yeah, here I put, so this is V, and this is Y, okay? And so the fiber over a point of X is a copy of V, so Fv, that's little, I guess. Fv over a point X, which is isomorphic to V, and inside of it we've got Fy over X, which is isomorphic to Y. And so this for all the variety X. Okay? Okay, so we relativize the model, if you want, over the variety X. Now we have to pull it back to the variety X. And to do so, we fix a section of this vector bundle. And that's P. Okay. Yeah. And we pull it back. So the definition depends on the model and on the section. So the Y degeneracy locus of S is defined by, so it's the set of points in X. Okay, it's the set of points in X such that, so S of X, so S of X is S is a map which goes from X to Fv, and S of X lives inside the fiber there. So we ask that S of X belongs to Fy over X. So this is inside Fv over X. So this is one inside V. Okay? So this is the definition. So another way to see it is as a scheme. So we take Fy inside Fv, and then we have the section S, and the degeneracy locus satisfies this Cartesian square. Okay. So some examples, maybe I'll write them here. So the first example is a trivial one. So we take G, just GL R, and V the standard representation, and Y is just the point 0, right? And so dy over S is the 0 locus of the section S. Okay? So the first interesting example is following, we choose G to be GLM times GLN. So this example will be the one of matrices. We take V, so the space of homomorphisms from Cm to Cn. And Y is a very classical locus, YR, so it is the rth determinantal variety. So the matrices defined by this condition, all the matrices of rank less or equal than R. Okay? And, okay, what happens in the relative situation? So in the relative situation, we have to pick a variety X, and then we have to pick a GLM times GLN principal bundle. So, but there is a correspondence between GL principal bundles and vector bundles. And so taking a GLM times GLN principal bundle is the same as choosing E and F, two vector bundles of rank M and N. Okay? Okay, but now it's easy to understand what V is. So FV is the space of homomorphisms between E and F. Okay? And the section S is just a morphism between vector bundles. And dyr of S is the degeneracy locus of a morphism between vector bundles. So these loci, these ones, have been studied, so they are quite classical in the literature, and yeah, they can be found in many places. I mean, you wouldn't expect maybe. So for example, the Veronese embedding and the Segre embedding, both of them give the degeneracy loci of morphisms between vector bundles. It's not difficult to see this. Okay, so this is classical. So I will give later some other examples, but there are even, I would say, many. Okay. Now I can write here. Okay, so now what we want to do is try to understand the geometry of this loci. The first thing is to have a result similar to this one, like Z of S smooth. But we cannot get the smoothness because the model in general is not smooth. For zero loci it is, but not in general. So we have the following proposition. So if the vector bundle FV is globally generated and S is general, then okay, dys is empty, or the codimension of dys inside X is the expected one, so is equal to the codimension of Y inside V, maybe. First thing, and the singular locus of dys is the degeneracy locus associated to the singular locus of Y. So sing of Y is a closed G-invariant subvariety. You can construct it. It's the degeneracy locus with the same section. So moreover, if Y is normal, then dys is normal. And this proposition is just apply the same proof you used to prove Bertini's theorem. It's just a generalization of Bertini's theorem. Okay. So. So now we are going to try to understand some other properties of this. Oh, okay. Yeah, I didn't say so. How to prove normality? So normality, it's a property that you can verify by looking at a resolution of singularities of y. So if the push forward of the structure sheaf of the resolution is the structure sheaf of the variety y, then it is normal. And so you can pick a G equivariant resolution of y, okay? And then you can relativize it using the functor f to a resolution of fy, and from that, from a base change argument, you can prove normality of the loci. Okay, so now I would say how to control the canonical bundle of dys. So, which is what we need to construct varieties with trivial canonical bundle, for example. So, in the case of matrices, the situation is known, is classical. So, I said we have S is a morphism between vector bundles. So, we can take, so let me call this D. So, E restricted to D, F restricted to D. We have a co-kernel sheaf and a kernel sheaf. Okay, so the relative normal bundle of the degeneracy locus, this is a classical fact, is this sheaf, the homomorphisms from K to C. So this is of rank, let me say rank M minus R, and this is of rank N minus R. So in general, if M and N are different, we don't know what the canonical is. I mean, it depends on either this or this one. One can use the exact sequence to compute the canonical bundle, but still one doesn't know what it is in general. But if M equal to N, one can compute using this exact sequence that the canonical of D, the relative canonical, is determinant of E dual times determinant of F to the power N minus R restricted to D. Okay? So in this case, we know how to compute the canonical bundle, and the canonical bundle is just the restriction of a bundle on X. So we can do the same game. I explained for zero loci and construct varieties with a trivial canonical bundle. So why this condition? And are there other examples of varieties Y for which we have this property? So there are two ways to try to understand what the canonical bundle is. So the first one, of which I won't talk about, I'll just say it. So one can try to construct a resolution of the structure sheaf of the loci. So use a G equivariant resolution of Y to construct a resolution of of OY, to construct a resolution of ODYS. So you can do it if Y is Cohen-Macaulay, and moreover, if Y is Gorenstein, so as an affine variety, then you have this property that the canonical sheaf of dys is the restriction of a line bundle over X. So this is a paper we're working on, and that should be ready soon. But here I won't talk about this thing. So it's related to, for those who know, to the Egon-Northcott. I mean, it's not related, but it's a generalization of the Egon-Northcott resolution. So here I will try to explain how to construct a desingularization of, so desingularization of this loci. So having a desingularization is useful for two reasons. The first one, we have desingularized, we have a smooth variety, and the second one will be clear at the end. So again, the idea is to start from something we know on Y, okay? So the idea is to take a G-equivariant desingularization of Y. But the thing that works better, so G-equivariant desingularization of Y. But the thing that works better is to take a particular desingularization, which is called a Kempf collapsing. Okay, so what is a Kempf collapsing? To define a Kempf collapsing, we need G over P, a homogeneous projective variety, which is the quotient of G by some parabolic subgroup. And so W will be a subbundle, subbundle of this bundle here. So G over P times V. So this is just a trivial bundle with fiber V. Okay? So we have a Kempf collapsing if, so you have Y inside V. Then we have the projection from the bundle. And here we have G over P, okay? Here we have W. So we have a Kempf collapsing, as I was saying, of this bundle over Y if this map factorizes through Y and if it is a desingularization. So W is just a smooth variety. So there is a chance to have a desingularization. Okay, why do we take Kempf collapsing will be clear after, but I just want to say that Kempf collapsing are quite natural in a certain way. So there are many Kempf collapsing in many situations. No, there are Kempf collapsing in many situations. So for example, for matrices, and also they are used when one wants to find a resolution of the ideal of Y. So this technique is called the geometric technique, and it's developed by Weimann and his collaborators. So let's see for matrices. So for matrices we have the variety YR of matrices of rank at most R inside the home CM Cn. Okay. And as we have to choose a homogeneous variety. So a general element in YR is a matrix with rank exactly R. So it defines, so its image defines a point in the Grassmannian R of R planes inside Cn. Okay. So this is G over P in this case. It's natural to consider this space. So here we have G over P times P. And the subbundle omega, W we need to consider is homomorphisms from Cm to the tautological bundle. Because this is exactly parameterizing the images of this morphism. So the composition of these two morphisms factorizes through Y, and actually it is a desingularization. It's a very classical desingularization of determinant of varieties. Okay, so other cases are yeah. So nilpotent orbits. So I will be just sketch about nilpotent orbits, and then I will give the main example of this talk. So here I'll start from a G over P directly. So we will construct a desingularization of certain varieties inside the Lie algebra of G. Okay. So it can be seen, it's not difficult to see that the cotangent bundle of G over P is a subbundle of this trivial bundle. And so we look at its image inside Lie of G, and this is a nilpotent orbit closure. So the elements in Y can be proven to be nilpotent elements inside Lie of G, and such a Y is called the orbit Y is called Richardson when there is this situation and when it is the image of such a collapsing. And so in some cases, I won't enter into in details. So in some cases, so let's say theta. Theta is a desingularization. Okay, so for quite a big class of nilpotent orbits, we have a Kempf collapsing. Okay, so it will be clear after why I'm giving these examples. And finally, so the other example is, okay, let's come back to the notation of the model. G, we take GL6, and V is wedge 3 of C6. Okay, and Y is the orbit closure of partially decomposable forms. So of elements in wedge 3 of C6, which can be written as V wedge sigma. So V is just a vector and sigma is a 2 form. Okay. So how to construct a Kempf collapsing of this Y? So you have wedge 3 of C6. So first you have to choose G over P. And G over P, so the natural choice is that every element here, generic element, defines a line inside P5. So we choose G over P to be P5. So this is G over P. This is G over P times V. And the bundle, the subbundle, this one to choose is, okay, the tautological bundle, which, I'm sorry, I denote by U, just to be coherent with that one. With the case of matrices, wedge C6. So this is W. And this can be written as wedge 2 of the quotient bundle of -1. And it can be proven that this is a degenerarization. So I gave all of these examples of Kempf collapsing just to convince you that they're quite natural in this context. And for example, there is a certain class of representations with finitely many orbits, which are called the prehomogeneous parabolic representations, for which, I mean, for I think almost all the orbits, there is a Kempf collapsing. So there, it's quite natural to consider these degenerations. Okay, yeah. So now what I try to explain is how to construct from a Kempf collapsing a degenerarization of the orbital degeneracy locus. Okay, maybe I'll just use this one. And I will do it in this specific example, but everything works fine in general. Okay. So just so that the notations are clearer, I will do it with this example. Yeah, sorry. Okay, so we have this Kempf collapsing. We want to relativize it over X. So we use the functor f. So we take our variety X. I didn't say, yeah. In the relative setting, we fix a variety X. So f, the G principal bundle, is associated to a vector bundle of rank 6. Okay, and fv is, as you would expect, wedge 3 of E. Okay. So here you have your section S, wedge 3 of E, and so to construct the relativization, we start by relativizing G over P. So in this case, P5 becomes just P of E. So the fibers, you have to think that the fibers have to remain those in the model, and then you're relativizing over X. So over this bundle, what you want to do is to relativize G over P times V, but V is a trivial bundle. So actually, when you relativize it, if this is theta, you obtain theta star of wedge 3 of E. So inside of it, you have the bundle W, which was wedge 2 of Q of -1. And this time, this Q and -1 are relative tautological bundles. And this sequence is still here. So you have this sequence, and you consider the quotient bundle, wedge 3 of Q. So you can believe me, this is the quotient of this map. Okay, so we haven't done yet. So the section S defines a section of theta star of wedge 3 of E by pulling it back. And then we can consider its class as a section of this bundle. So we call it S tilde, P of E, wedge 3 of Q. Okay. Okay. So here we have our degeneracy locus, and here we can consider the zero locus of this section S. Okay. So the theorem is that if Phi is globally generated and S general, then Z of S tilde is the singularization of dys. Okay, so this is theta. Okay, so let's say the proof, at least an idea. So Z of S is smooth because it is just a zero locus of an enough general section. Then we want to see that theta restricted to Z of S tilde factorizes through dy of S. Okay, we have such a morphism. Okay, but this this should be clear after I did the following diagram. So we've got wedge 3 of E, and here we've got wedge 3 of E, P of E, and we've got Fy. So Fy is desingularized by wedge 2 of Q of -1, just because you have to look at the fibers, and over each fiber, this desingularizes Fy. So the section S, we have the section S here and theta star of S here. So S tilde is 0 exactly on the points where the section theta star of S goes inside wedge 2 of Q of -1. Okay, so exactly on the points that are projected onto the points of X, which are sent by S inside Fy. So this says that the theta restricted factorizes, and then because S is general, one can prove that theta restricted is a desingularization. Okay. Okay. So why this desingularization is interesting? Because of the following corollary. So in the same hypothesis, let's assume that Y is normal. Then so I said this works for any Kempf collapsing. I did it in this case, but it works for any Kempf collapsing. And the corollary too, so I just come back to W and G over P. So if the determinant of W is equal to the canonical of G over P, and this is a crepancy condition in the sense that this resolution becomes crepant, then, so the relative bundle of this resolution is the trivial bundle, then the canonical of dys is just the canonical, is just the restriction of a line bundle over X over dy of S. So L is a line bundle over X. Okay? So this is exactly what we wanted to obtain. So if we have a crepant Kempf collapsing, then the canonical bundle of the degeneracy locus is just the restriction of a line bundle over X. So what about these examples? So you should believe me. So it's just a computation. So how do we prove it? So this is at zero locus, so just by adjunction. By adjunction, we prove that the canonical bundle of the zero locus is the pullback of a bundle on X. And then we get this result. So in this case, this Kempf collapsing is crepant exactly when M equals to N. And then using adjunction, one finds this same formula. So what about these two cases? So the first one, it's clear that the condition is satisfied. So we can compute the canonical bundle in this case. And in this, in the case of nilpotent orbits. And in this case too, we have the determinant of wedge 2 of Q of minus 1 is O of minus 6. So it's the canonical bundle of P5. So let me stick to this example to give some applications. So we obtained that in this case, the canonical bundle of the degeneracy locus is the canonical bundle of X times the determinant of E to the power 5 restricted to dys. Okay? Okay, so now if you want to construct, for example, Fano fourfold, a Fano fourfold using this, which is a Y degeneracy locus, where Y is this orbit. So what do we need to do? So something I didn't say, that the codimension of Y inside V is 5, and the codimension of the singular locus of Y inside Y is 5. So when we construct Fano fourfolds, we obtain something at the degeneracy locus which is already smooth. So we need a variety X of dimension 9, 5 plus 4, and E a vector bundle of rank 6, globally generated, such that, so we want the kx times determinant of E to the power 5 is so minus this bundle is ample. Okay, and so if I have time, just to give some applications. So we used this orbit and some nilpotent orbits to construct many Calabi-Yau fourfolds, and also some Fano fourfolds and threefolds, and even not smooth singular Fano threefolds by using some nilpotent orbits. And so I just want to say that there are some examples which are inside. So X, you could take the Gorenstein, for example. Just let me give one example and we'll finish. 3, 6, and you can take as E U star plus 3OX. Okay, you can verify that it satisfies that equality. I mean, it satisfies that condition. Or you can take an hyperplane section inside the Gorensteinian 2,7, and you can see that you can have E equal to dual of the tautological plus 4OX, or the quotient plus 2 OX. And actually using some computer, you can compute some invariants of these Fano varieties, and you can realize that, so there is a classification for Fano fourfolds inside Grassmannians, which are 0 loci, and by Oliver Kuchle. And he computed also some invariants, and you can verify that these orbital degeneracy loci are not in the classification. So it's an indication that they're not 0 loci. Okay. So thank you.
Are there any questions or comments, perhaps?
Yeah, so in your example, for example, there's a choice of section, right?
Yeah, yeah.
So if you vary the section, you get moduli, or you get...
You get a family, yeah.
And can it change, really? For example, the automorphism group, or...
We haven't studied the automorphisms group, but it's true that maybe all this, we have a lot of information on these loci. So yeah, you can understand more or less which is the dimension of the family. So this can be done, and so if you let the section S vary, then you get a family. Yeah, you can understand more or less what is the group.
So do you have any idea if these examples are stable?
No. No, I don't.
Okay, so let's say I figure again.